So today we have two lectures. One's on computational thinking, and the other one is on decomposition. I'm sort of breaking, I think it's on decomposition, because the computational thinking we'll see in the slide number 3. I can see it coming up there in slide number 3. Computational thinking, there's 4 areas that we concentrate on. And I think the first one is decomposition, which is just about breaking things down into smaller, easier chunks so that we can work on them. So as we go through this lecture, I think what you really should do is you should sort of just apply whatever else you've sort of learned in your life so far. A lot of it is, this is not sort of very abstract. What I mean by that is your own experiences will have, you'll know these things just from your own experiences. A lot of this is practical sort of understanding, I think. But anyway, so we have this term, computational thinking. That's actually like a theme of this course. And actually the book which we say is the textbook, which is not really so much the textbook, but that book is about computational thinking. And the idea of this term computational thinking is newer than the idea of using computers, actually. But basically, there was an academic by the name of Jennifer Wing. She wrote a article about computational thinking, which will be shared with you later in the course. But the idea of computational thinking, as the slides say, and as I say, there may be. So let's look at the. Oh, is that? I think I need to make that a little smaller, just so we can see it. Yeah. So the idea of computational thinking doesn't have to apply to computers, but the idea is, as it says there, solving a problem in a way such that perhaps you could use a computer to do that, or to help you with it. The thing about computational thinking is it includes more than one idea, and so we have different components of what we do to include in our computational thinking. But it allows us to take a complex problem. And the first point there is understand the problem, and then come up with possible solutions, present these solutions in a way that a computer or somebody or a human could be used to solve the problem. Now, a computer can't solve the problem, but because remember, computers only do what we tell them to do, but we could maybe tell the computer to do what we think will solve the problem. So I mentioned a minute ago that our computational thinking, we have components of it. In your quizzes, tests, exams, each of these terms, you'll be asked something about it. So, I mean, there'll probably be a multi-choice question, which will say, decomposition is, and you got 3 or 4 different ideas, and which one of those? Or you'll have an idea, more likely, you'll have an idea. So you'll have a multiple choice question, which will say, looking for similarities within problems. A, decomposition. B, pattern recognition. C, abstraction. D, algorithms. And then you'll have to choose, oh, well, the right one is B. You get the idea? So you do need to know these terms and be able to sort of relate to them. Now, the diagram on the right there actually kind of helps too. I think those I should turn off my phone, right? I think my phone is telling me it's time for coffee. No. No, it's not. So decomposition, abstraction, algorithms, and pattern recognition. We see these little sort of diagrams beside those. I think if you look at those diagrams, they might actually help you to understand what the terms mean, because the diagrams are quite useful there. Anyway, so we got decomposition. That's our first one here over on the top left. And what we see is we see a big idea with a question mark there, something complex. So a complex problem that may be too big for us to sort of just handle it as it is. So what we do is we break it down into smaller pieces. That's decomposition, taking a big problem, breaking it down into smaller pieces. And we see that, and we end up with these smaller pieces, which may still be too big to handle. And so we continue that until we get to components, which each individual one of those components is solvable. And then we solve those problems, and then we combine our work, and eventually we find that we've solved the entire problem. So decomposition is not just used by IT people. None of these ideas are used just by IT people. But this is a sort of a common way that people approach problems. if you were doing a large paper here at the college, you know, you had a big project that you had to do, you would probably approach it this way if you wanted to actually be able to do it, right? So you got a project with many parts. You're going to take it and break it down into smaller parts and solve those parts individually. Abstraction, the idea of abstraction is when you have a lot of information which some of which is useful to your solving of the problem, but not all of it is. The idea of abstraction is just to focus on the things that you need to solve the problem. And in other words, it's to actually remove unneeded information. So abstraction is that kind of an idea. Abstraction is what we do a lot in science, but particularly in mathematics. Everything that you've ever done in mathematics, I would say, would be abstraction, right? I mean, you know, they'll give you a problem like, you know, two children go to the store. You know, one is traveling at 4 kilometers an hour, one is traveling at 5 kilometers an hour. You know, how far did they travel? That type of thing, right? And so, I mean, you know, you would do a x equals 5 plus y, you know, this type of thing, and x equals 4. You get the idea. So that's abstraction. Algorithms, I guess that's kind of, by the time we get to algorithms, we're on our way to solving a problem computationally, but the idea of an algorithm is step-by-step process. Now, remember in earlier lectures, we actually talked about cooking and a recipe as being an algorithm. So that's a day-to-day experience that we have with algorithms, but we also use it a lot in computing. The next one there, pattern recognition. If we see things that repeat somehow, that is a perfect situation for developing a general purpose sort of, we would call it a module, a function that we would use. So we would write a function in a program, which is sort of a subset of that program, which we could use over and over again using different inputs. I will try and show you that this week, maybe at the end of this lecture, if this lecture doesn't take too much. Now, I'm sorry that the way we're looking at this may be a bit strange, but that's because I want to make sure I don't miss out on these notes at the end, because there may be some notes, and yeah, they may be useful. So a complex problem, it's very hard to solve it from what we see. So what do? We try and break that problem down into smaller pieces. That's called decomposition. And maybe those smaller pieces that are at a level where we can solve them. Maybe they're not. I mean, if you looked at that diagram before, you would have seen the one big circle going into smaller circles. And actually that process was repeated until we got to very small circles. Those ones represented tasks that we could actually solve. So decomposition might be more than one step. You might have to decompose one big problem with some smaller problems. They're still too big to solve, so decompose them again. Eventually we get to something which is small enough to solve. We solve that, and then we sort of put all of our solved components together to build our big solution. Pattern recognition, I just mentioned. If we see something that seems to be repeating, that is a good candidate for some kind of module. I refer to it as a general purpose module. And, you know, so in mathematics, we remember the problem that we had, which was the blocks, you know, and the blocks, the L-shaped blocks, remember that? We recognized a pattern there. And after we looked at that and recognized the pattern, we were able to actually represent that in an abstract way as y is equal to 2x plus 1. Remember that? So because 2x, because we had to add the sides, and then we had the corner, that was the 1. So that is a pattern recognition. Mathematicians do that. IT people do that. When we do it in IT, we're going to produce a little module to do that. Abstraction, as I mentioned, we find out what are the important details, kind of like filtering, I guess you'd say, and leave behind the things that aren't important. So we're taking away things that are not important, so we get something simple to work on. Now, all of these things, you might say, oh, well, Mark, you just sort of, I don't really understand what you're saying there, Mark. That's fine, because each one of these we will look at in detail. So like we got a lecture on each of these. So we'll look at each of those in detail and spend a bit of time on it. Algorithms, I think I've already sort of mentioned. Remember the recipe? That's an algorithm. And from an algorithm, algorithms are ideal for us writing little programs. So an algorithm might represent a module that we've developed from pattern recognition. And we may have algorithms for each of the individual little things that we've done from our decomposition. We put those together as a general program. Okay. So computational thinking is something that humans do. Humans do computational thinking. Computers don't do computational thinking. So even though computational thinking, welcome, has the word computation, sounds like computing, right? Yeah, maybe you could pass that around. Take it with you. Take it with you, and pass it around to as you go. Well, what I mean by that is computational thinking is done by people. You don't have to be in computing to do computational thinking. Yeah, so computational thinking, when you know exactly what you want the computer to do, then you can give it instructions through a computer program. You would have to have some computational thinking in your mind before you did that. You could have computational thinking which had nothing to do with a computer, though. I mean, you know, just you're solving your problem. You know, the car won't start. You know, so what do I know about cars that I could apply to sort of solve that problem? All right, so you know that the car not starting might be a complex problem, which I would narrow down by smaller steps. So that would be decomposition, and then and those steps I might actually have a checklist, which would help me to sort of identify the thing where the car wouldn't start. But that could be computational thinking without using a computer. Okay, so we've got an example. All right, so you're going to meet your friends at a, I suppose at a restaurant or something like that. You want to get to that restaurant. So you know where that restaurant is, or somebody sends you a link. And of course, you skip all of this, don't you? Because you just use Google Maps, start, and it goes there. But okay, somebody had to write the algorithm to do that for Google Maps or Waze or whatever. Now, supposing you didn't have that, you know, so some computational thinking went into that. Supposing you were designing Google Maps, how would you design the Google Maps so that they tell you that you're going to go to this place? Then how do you know? Well, you could do it in a step-by-step fashion, and you could do that actually working backwards. So I want to get to this point. You know, what's the traffic like here? What's the traffic like there? How are these roads? And you could have you could apply your own sort of filter to it. So as it says there, you might want to go in a way so that you avoid all the speed bumps. That might not be the fastest way. You might want to go in a way so that you avoid all the toll roads. You know, maybe we don't have toll roads here in Qatar yet, but I think they're going to happen. I think I've seen something up. They're going to put them. You might want to go. Oh, you dropped one. Oh, sorry about that. You might want to go in a way that is the shortest time, or you might want to go in a way which is the shortest distance. So depending on which way you want to go, you could work backward or forward through that, but you could have a step-by-step process of going there. Before you left, you would be thinking about that, maybe planning how you're going to do it. And that is, in fact, a form of computational thinking. And we know that that kind of computational thinking on how to get somewhere, we know that that can be used by a human being to instruct a computer to do it. Because I just mentioned, we can just go to Waze, or we can just go to Google, and it will tell us how to do it, because somebody has actually written the programs to do that. And you can be sure that those programs are actually really quite complex. I mean, it just looks like something simple on our phone, right? It draws a map and says, do this and turn this, turn that. It's quite a lot of complex programming. And yeah, they had started, there's all kinds of inputs that go into that. And that's why there's so many nice jobs in those places like in San Francisco, where Google, et cetera, is. They have a lot of programmers there, a lot of very smart people working to write those programs and get them so that we can use them. And you might say, oh, well, there's all those computer programmers there working in Silicon Valley, and they're making lots of money, because they do make lots of money. I mean, you know, they're young people earning a couple $100,000 a year or more. So why are they so? But it's free. I get to use Google Maps and it's free, so how does that work? Well, it's not free, is it? Because whenever you use their product, they get information about you. And so, I mean, you're paying for it by being present on the by being available to their data scraping, I guess you could say. So they get information about you. They know who you are. They know how old you are. They know where you go. They probably even know what you buy. And so from that, they can sell information about you to people that want to sell you stuff. And then you will find that, after you'll find that you get a message saying, do you want to buy this? It just happens to be something that you look for while you're in, so that's why it's free, if you were wondering. It's not really free, but most of us sort of think that that's a reasonable trade-off. I don't mind them giving me adverts to buy things, and I'll use their free Google Maps, right? Just like Facebook, it's the same thing. They what they want is they want to know about you. So far, I haven't got any notes, but there may be some. Decomposition. So we have a problem. What's that? So we use problem. It's in the name of this course. This course is called Computational Thinking Problem Solving, right? So what is problem solving? I gave you an idea of my idea on that when you have your car and it's not working. So what do you do? I think as humans, we like problem solving, right? I mean, this weekend I went down to the desert with my wife, and then I went out riding a motorcycle. Sometimes we go down there and nothing happens. Sometimes we go down there. This weekend, one car rolled over onto its roof. A few times I've broken things on my motorbike. And, when those things happen, you might say, oh, that's terrible. But actually, what happens when that is in your mind, you're like, oh, problem, solve. And it's kind of fun. I mean, why do we keep going in the desert, right? Like, I had a friend when I was in Dubai, and, the saying that we used to have is, don't take anything into the desert that you're not prepared to leave there, right? I mean, if you can't afford to leave that car there in the desert, don't take it. Because, it just happens, right? Where you go out there and the cars break down, people get stuck. And it's kind of fun, especially just the simple ones like people get stuck, right? People get stuck, that's fun. How do we solve that? And so that's a nice little challenge. And, different people have different ways of doing it. Maybe we'll pull it out, maybe we'll lift it up, maybe we'll dig. But there's a problem solving process that goes on, and we enjoy it. You might say, oh, that's a big problem. Wish I didn't have the problem. Well, if you didn't want a problem, why'd you go? Of course you wanted the problem because it actually challenges you and you feel better for solving the problem. That's what we do. We need a challenge. I mean, you came to the college, you have a problem, which is you want to have a piece of paper, right? It's not easy. There's this problem of you getting that piece of paper is a complex problem. You have to break it down into lots of little small bits, right? One of those small bits is this class. Then there's another one, which is your IELTS, right? And then there's another one, which is your mathematics, all of these small problems. And those problems are smaller than the piece of paper problem, which is a big one. But each of those classes is made up of lots of little problems too. And we enjoy it. Problems are good for us. It keeps our mind happy. Happy is not the right word. It keeps our mind growing, I guess you'd say. And that's a good thing. So here's a problem. People are getting this disease. It's called COVID-19. And the problem with that disease is people couldn't breathe because the disease was infecting their lungs. And so that's bad because you have to take them into the hospital and put them in ICU and put them on a ventilator. And that could be a really bad problem if too many people were in a hospital at the same time, because then you run out of ventilators and, then somebody's maybe going to die, because they can't breathe. So we wanted to not let this spread too fast. We wanted to slow it down so that when people do arrive at the hospital needing a ventilator, that care was available to them so that they didn't die. So we had to stop it from spreading. Well, what could we do? Well, we could do social distancing. We could stop people contacting people that have the disease. We can find out people who have the disease and we can separate them from everybody else. We call it quarantine, right? So we have some people in this class probably that aren't here because they're on quarantine. Because the new variant, what is it called? Omicron. Omicron spreads really quickly. And so, those people get the disease, and we don't want it to spread too fast because we don't want the hospital to be full of people who can't breathe. And so they came up with this, this app that we have on our phone that we have to show people that we don't have the disease, right? And that works quite good. And the other thing about the app, I suppose, if you contact, one of my colleagues here, I have teachers that, colleague friends, who, one day they just received a phone call from the security here at the college. Could you please come down and do a rapid antigen test? Now, I don't know how that works with this, but because they had been in the same room with somebody who had COVID, then they had to be tested to see if they had COVID. And, I came back from holiday, and my ethras was green when I arrived home. And, I got one of these sort of things from the I don't know, I gave it to the airline that said that I was okay to come home. And I just walked out of the airport, and like the next day, my ethras went yellow. Then I found out, you're supposed to do a PCR when you come out. Okay. So, I mean, so all of that information is sort of tracking you as you go. So, I mean, that's a good thing. Now the ethras thing, it wouldn't be fair to say that there was some really smart people here in Qatar that just sat down and dreamed up ethras on their own. They would have, what it was is there was some really smart people who looked at how this could be solved with technology and actually found some things that were happening around the world. Like China had an app that's kind of like this, and they came up with an app based on ideas like that. Abdurrahim, welcome. So when you have the big problem, like I said, you got a big problem, which is getting yourself a qualification. Where do you start? Well, yeah, we help you with that because we break it down. We've actually done the modularization. But where do you start in this class? I mean, you got a problem this week, which is a quiz, right? And you have had an assignment last week, that problem. So the quiz problem that you got this week, which is going to be the last lesson time in this week. How are you going to solve that problem? Well, probably you're going to organize your notes. You're going to read over them. You're going to look at the problems that you've done, see if you can solve them. And each of those you'll do sort of one at a time until you're satisfied that you're sort of prepared with it. The big problem is being prepared. Little problem is each one of those steps, right? So how do I revise lecture 1, lecture 2, lecture 3, lecture 4? How do I revise those labs? And then eventually you find yourself ready. So that's decomposition. You're faced with a complex task and you break it down into smaller tasks. Like it says there, this is not just something that you would, probably better put that in just in case somebody else comes. Oh, look at that, Frank. So the artistic mind, I mean, this is the point of this slide is computing. We call it computing science, but it's not just science, right? It's great for people to be involved in this, and people are not just scientists. They also have sort of what's the word I want to say? I want to say artistic, but they like to develop new ways of looking at things. I guess, yeah, artistic. I suppose there's an artistic side to them that is creative. Yeah, that's the better word. It's creative, that they like to do things in new ways. That's a very good sort of attribute to bring to computing. And so computing, I think, can be the perfect sort of joining of scientific and artistic thinking. You can do a lot artistically in computing. Think of a computer game, but also the way that you solve problems. Creativity, meaning that you come up with a solution which is, nobody ever thought of that before. And sometimes that can be a really, really good thing. So we use these ideas. So strategies means looking over to a long-term solution kind of thing. Heuristics, try and error. Heuristics is about doing things by practice. Try this, try that, and getting something that kind of works. As opposed to just doing things in a rigid scientific sort of physics, chemistry, biology way. You know what I'm saying? Yeah. It's not just about electronics, if you like. It's also about these other ways of human thinking. So I'm on the right slide. Yeah, all right. So this fellow by the name Polya, Hungarian mathematician, apparently. So I mentioned it's 1945, which is kind of strange because his book is actually from 1973. So maybe that's just a later edition of it. But I mean, if you look at this and you look at this, on the left, we have what we call a scientific method. Scientific method has been basically in this format for more than 1,000 years. I mean, you know, the ancient Islamic universities in Morocco, etc., they're using this pretty much. The Greeks were using this. I mean, Aristotle, you know, was using this. 2,000 years, I suppose. The one on the right is Polya's sort of interpretation of that for computing developing. So yeah, okay, so form a hypothesis means I noticed there's something out there in the world, and this is this phenomenon that's happening, and I think this is the reason. Me saying, I think this is the reason, that's my hypothesis. Okay, so how can I show that what I think is the reason is the reason? Well, I'll design some experiments to show that, well, this couldn't be the reason. So we have some, and this couldn't be the reason. And I'll try and prove that my reason that I think is the reason can't be the reason. If I can't prove that it isn't the reason, then maybe it is the reason. I mean, that's how we do it in science. We execute that experiment. We might repeat that experiment many times. We evaluate the results. We publish the results. We ask other people to test it. And if nobody can sort of disprove our idea, then we have more or less satisfied our hypothesis. Now, what we do in computing is going to be a little different because we're not trying to prove something. We're trying to, or disprove something. We're trying to solve a problem. So it has to be slightly different than the scientific method. But you'll see that the steps are kind of similar, right? We have a problem. So first thing is, how do I understand the problem? Isn't that kind of like, I think this is what's happening? It's kind of like that, right? So it's kind of like the scientific. Then we devise a plan. Here's our problem. I'm going to have that. My plan, my multi-step plan has many steps in it. How I'm going to solve that problem. Then I execute the plan. Then I review and extend. Maybe you'd like to be a project manager one day. I don't know. It's a natural progression for some people in the computing industry to be a project manager. I have a daughter and a son-in-law who are both project managers. Nice jobs, you know, nice money, nice jobs. And yeah, this is all they do all day, right? They understand problems that break. They don't actually write any computer code. Isn't that weird? Right? I mean, all they do is design. This is the steps we're going to take to make this program work. This person's going to do this, that person's going to do that, and then they check up. It's a form of management. That's why it's called project management. If you were excellent in those things, maybe that would be the thing for you. There's a project management course that you do as part of your degree here as well. So look at that. Yeah, I highly recommend it. My daughter makes a lot more money than I do, and so does my son-in-law. Project management, totally recommend. So yeah, don't panic. Yeah, so it may seem big. Basically, what's that old saying? The journey of 1,000 miles starts with this first step. That kind of thing, right? So yeah, you can't do it all at once. If you've broken it down into small enough steps, just take it. Just take that first step. Don't be put off by the size. Big problems can be broken up. And the other thing is, as it says, we see a problem and we might want to just jump in and start writing code. That's what it means by solving the problem, right? We see a problem. We know that we can solve it using our Python programming language or whatever, or maybe we can't, you know, maybe it's better to use a different tool. And so that's the problem if we try and just jump in and solve it without sort of really analyzing it first. This has been an age-old problem in computing. The analysis phase needs to come before the development phase. You really have to understand the problem completely, as much as you can, as much as you have time to, before you start writing code. If we don't really understand it perfectly, then we find ourselves having to do a bit of rework usually. We have to do things over and over again. So yeah, we need to define the problem. We have to really understand what is the goal. Now, usually we're going to be developing some kind of a solution that involves other people. So this is going to require a lot of communication. And so we have a term for that. We call them systems analysts, business analysts. So programmer analyst. So a programmer analyst is going to be a person who talks to their customer about what their problem is, understands the problem completely, and then presents a solution which involves some computer programming. So you saw, I hope in that understanding that a lot of time is actually spent on understanding the problem, especially nowadays. That person may be the same person who is the analyst and the programmer, because the tools that we use for developing solutions, they're actually quite rapid in their development. We can actually, once we understand a problem, it doesn't take very long to get the code together to sort of solve it. Much quicker than it was sort of 20 years ago. Our tools are much more rapid. And so we need to spend a lot of time on actually just understanding it. And as I said, that's going to involve talking to people. It's going to involve sort of thinking carefully about the problem that we have. As it says, developing the goal and making sure that we're solving the right problem. All right. So Paulia says it's foolish to try and answer a problem that we don't understand. Restate the problem in your own words. Talk to them about it. Restate the problem to them in your own words and get their feedback on it, I would say. Try to represent the problem using pictures and diagrams, then show that to them. That's systems analysis. We draw some problem. We have a problem. We talk to the user about it. We draw some diagrams, and then we take the diagrams to them. We explain the diagram, and they'll say, "No, this is not right," or they'll say, "Oh yeah, that's all right." Then we know we're on the right track. There's knowns and unknowns. Yeah. So if we have enough knowns, we can get started on that. Remember, so in purple, I suppose, is really important. So that's highlighted. So let's look at that carefully. Whatever the problem, the key thing to remember is the goal to find what needs to be done and not how it should be done. So what's the old saying, give a person a hammer and then everything looks like a nail, right? So just because you know how to program in Python doesn't mean that every problem needs to have a Python program written for it. That's the idea. Maybe there's some other tool that you should use. Considering goal, ask, how do you know when the problem is solved? That would be the goal. How do we know when what we've got is what we're supposed to have? How do we know when we're done? Very, very big problem in computing is that, so we have specification creep. We call that, right? We start off with a problem, and either the computer programmer or the user keeps adding things. All right. So basically, yeah, before we start, we have to say, well, this is what we want to have when we're finished. When we're finished, it'll look like that. If we don't know that, then we really shouldn't start. All right. So you're going to go to a conference, and you want to know, well, what are we going to have? What's this? Take 1 minute to think about how to define the goals of a conference. So this would be you planning the goals of the conference. So I guess the idea is, do we need to, if we're planning our conference, and maybe the conference is a couple of weeks out, which one of these things do we need to do now as we're planning the conference? Which one of these things can we postpone until kind of like the conference starts? So which one of the things would we do first, do you think? Just looking at that, the idea is, I think, here to put these in the order in which we would try and solve them. Dinner or light snack, could we postpone that? Let's imagine that this conference is 3 months from now. I would postpone the dinner or light snack, right? I mean, I'd want to know what is our conference about first and who's going to be coming. Anyway, so this is what I mean by that. We'd want to know what is the topic of our conference, I think that's where I'd start, right? I think I'd start with, well, if I'm going to have a conference, I have to know what it's about. Then I can know who I'm going to invite. You know, then I'd sort of do this. Then once I've got the guest speakers, then I can start inviting people. Then I could know how many chairs. Then I would maybe know where I'm going to put people. Oh, so, yeah. And I think I'd leave the snack until later. I mean, I think you could have a successful conference and you could have shrimps or you could have shawarmas and nobody would really care. You know what I'm saying? It'd be all right. But they probably would care if they were at the conference and they wanted to know about cybersecurity, but you had a conference about, I don't know, about big data or something, you know, that type of thing would be more important to sort of nail down first, I think. All right, so if the end of the goal is complicated, what? Writing specification, developer specification. The purple is highlighted, so that's important to help you better defining your problem goals. Write them as though someone else will eventually have to do it. So a lot of times in computing, we'll do this afterwards. We'll write a document, which is a specification of our work so that somebody can pick it up and change it as time evolves so that the product has some life. But definitely, if you are solving trying to solve a problem and you have to keep in your mind the fact that you might not be there because you might be assigned to a different project, or once the project is finished, you know, you move on or whatever. So you have to imagine that somebody else would have to be able to read your specification. That's all that means. All your specification, everything that you write about your problem should be written in a way so that somebody else could just pick it up and do it. That is the end of that lecture, which is lecture number 5. So what I'm going to do is I'm going to turn off the Zoom.